Today we're talking about one of the most fundamental things in the universe, waves. Everything from the music you hear, to the light you see, to the Wi-Fi that's probably delivering this video is a wave. We're going to focus on two key testable ideas. First, the math. How do speed, wavelength, and frequency all relate? And second, the big one. How does a wave's energy relate to its frequency? So, what is a wave? The biggest mistake people make is thinking that stuff moves with the wave, but it doesn't. A wave is a transfer of energy. The classic example is a stadium wave. The fans stand up and sit down, and the wave of energy moves around the stadium. But the fans themselves end up right back in their original seats. They just transferred the energy. A duck sitting on a lake bobs up and down as a wave passes, but the duck doesn't get carried to the shore. The energy does. To talk about waves, we need to know their properties. The first is amplitude. The amplitude is just the wave's height, measured from its at-rest middle line. But what amplitude really tells us is the wave's energy or intensity. If you're listening to music, a high amplitude sound wave is loud. A low amplitude sound wave is quiet. For light, a high amplitude light wave is bright, and a low amplitude one is dim. Next we have wavelength. This is the one we use the Greek letter lambda for. It's simply the length of one full wave. The easiest way to measure this is from one crest or peak to the very next crest. You could also measure from one trough, the bottom, to the next trough. It's the physical distance, in meters, that the wave pattern takes to repeat itself. The third property is frequency, or F. If wavelength is the length of the wave, frequency is how often it shows up. We measure it in hertz, which just means cycles per second. If you're at the beach and one wave hits the shore every second, the frequency is 1 hertz. If 10 waves hit the shore every second, the frequency is 10 hertz. A high-frequency wave is a very fast, wiggly wave. Finally, we have wave speed, V. This is just how fast the energy is moving in meters per second. Now, this is a critical concept. The speed of a wave is not set by its frequency or wavelength. It's set by the medium, the stuff it's traveling through. Sound travels at one speed in air, a different, faster speed in water, and an even faster speed in a solid like steel. The medium is in charge of the speed. This brings us to the most important equation of this unit, the wave equation. It's V equals lambda F. The speed of a wave equals its wavelength times its frequency. This is the mathematical rule that connects all three properties for any wave, whether it's a sound wave, a light wave, or a wave on a string. This is the computational model that standard HS-PS4-1 is all about. Let's think about V equals lambda F. In any given medium, like light traveling through space or sound traveling through the air in your room, the speed V is constant. It's locked in. So lambda and F are on a kind of seesaw. If you want to keep V constant, and you make the frequency F go up, you must make the wavelength, lambda, go down by the same amount. This is an inverse relationship. A high-frequency wave must have a short wavelength. A low-frequency wave must have a long wavelength. We can split all waves into two big families. The first is mechanical waves. These are needy waves. They need a medium, a solid, liquid, or gas, to travel. Sound is mechanical. If you scream in space, there's no air to vibrate, so no sound is made. Ocean waves and earthquake waves are also mechanical. The second family is electromagnetic EM waves. These are special. They don't need a medium. They can travel through the total emptiness of a vacuum. Light is the perfect example. Electromagnetic, or EM waves, are how the sun's energy gets to us. They're made of oscillating electric and magnetic fields. But here's the key. In a vacuum, all EM waves travel at exactly the same speed. We call this the speed of light, and we give it the letter c. It's about 300 million meters per second. This is the ultimate speed limit of the universe. So for all EM waves in space, our equation becomes c equals lambda f. Since all EM waves travel at speed c, the only thing that's different between them is their lambda and f. We've organized them all into one big chart, from lowest frequency to highest. This is the electromagnetic spectrum. It includes everything from radio waves that are miles long to gamma rays that are smaller than an atom. And that tiny, tiny sliver in the middle, that's the only part we can see. We call it visible light. On the far left of the spectrum, we have the long wavelength, low frequency waves. These are radio waves. They are great for broadcasting information over long distances, like your car radio. A little wigglier, higher frequency, are microwaves. We've cleverly harnessed these to do two main things: cook our food by making water molecules vibrate, and communicate with our Wi-Fi routers and cell phones. Moving up, we get to infrared, or IR. Infra means below, so this is the wave below red in terms of frequency. You can't see it, but you can feel it. Infrared radiation is heat, the remote control for your TV, thermal imaging night vision goggles, and the heat lamp at a restaurant all use infrared. Right next to it is the sliver of visible light. It's the rainbow, from red, lowest F, to violet, highest F. Roy G. Biv. What's beyond violet? Ultraviolet, or UV. Ultra means beyond. These waves have a shorter wavelength and a higher frequency than the light we can see. This means they have more energy. This is the first wave on our list that's energetic enough to be dangerous. UV from the sun is what causes sunburn and skin damage. But it's also useful. We use it in tanning beds, as a black light to make things glow, and to sterilize medical equipment. Keep going to higher frequencies, and you get to the really high energy stuff. X-rays have such a high frequency and short wavelength that they can pass right through your skin and muscles. But they get stopped by your denser bones. This makes them perfect for medical imaging. At the very top, with the absolute highest frequency, are gamma rays. These are given off by nuclear reactions and cosmic events. They are extremely energetic and dangerous, but we can also use them in a controlled way to destroy cancer cells. This brings us to the second and most important big idea of HS-PS4-1. There is a direct relationship between an EM wave's frequency and its energy. It's simple. High frequency equals high energy. This is why the EM spectrum is also an energy spectrum. Radio waves and microwaves have low frequencies, so they have low energy. They can pass through us all day long without any harm. But UV, X-rays, and gamma rays have very high frequencies. So they carry a lot of energy, enough to damage or destroy living cells. All waves, mechanical or EM, also have behaviors. Reflection is the simplest. It's just a wave bouncing off a barrier. A sound wave reflecting off a canyon wall is an echo. A light wave reflecting off a smooth silver surface is a mirror. It's a very predictable bounce. Refraction is a bit trippier. This is the bending of a wave when it goes from one medium to another. It bends because the medium change causes a speed change. The most famous example is a straw in a glass of water. It looks like the straw is broken or bent. It's not. The light waves from the straw are bending as they go from the water, a slow medium, to the air, a fast medium, before they reach your eyes. This is also how a prism works. Finally, diffraction is a wave's ability to bend around a corner or spread out. This is why you can hear your parents talking in the kitchen even if you're in the living room. The sound waves, which have a long wavelength, can easily bend and spread around the doorway. Light waves have a tiny, tiny wavelength, so they don't diffract as much. That's why you can hear them, but you can't see them. So let's sum it all up. All waves transfer energy, and they are all described by the mathematical relationship V equals lambda f. For EM waves in space, their speed c is constant, so their wavelength and frequency are inversely related. And most importantly, an EM wave's energy is directly related to its frequency. A high-frequency wave, like a gamma ray, is a high-energy wave. A low-frequency wave, like a radio wave, is a low-energy wave.